Why, hello, friends. Jen Foxbot here for another edition of Math Mondays. Da 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 da. Yeah! All right. So, in this episode, we are going to tackle second order derivatives. It's okay. Don't worry. Just like the first part, which is called derivative calculus. So, if you're like, wait, what is a second order derivative? Check out part one. That will definitely help. But just like we did in that video series, we are going to really focus on understanding what a second order derivative is, and then use the same type of simple real world scenario to help us understand what this particular symbol means. I'm also going to talk a little bit about the couple of common types of notation because math is a language. There are different symbols. Sometimes the symbols mean the same thing, and that can be very confusing, especially if you're just getting introduced to it. So I will try to be very clear about what the different symbols are and what they mean. And then I'll let you pick, going forth in your math adventures, you can pick what type of notation you really like. So this is what the Leibniz notation for a second order derivative, full derivative. I'm not going to talk about partials. Don't worry about that if you haven't heard of it. It's not relevant just yet. But anyway, so this is the Leibniz notation for a second order full derivative. So the way that we can think about this is like all we're doing is taking the derivative of a derivative. So that's kind of how we can piece this out. And so then when we combine them, we get d squared dx squared of our function f of x. So the way that I like to read this is like left to right and then top to bottom. So we're taking the second derivative, d squared, with respect to x. So the reason why you put the 2 after the x here is because it is these little pieces of x. So dx really basically means like a tiny little piece of x. So if you have like a function here and it's like blah, 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 and this is x, dx is like tiny little slices. So if you want to learn more about that, check out the video I did on area, which talks about those little slices of x. So that's what dx actually is, and that's why the square goes on the outside. So I also want to point out that the variable on the bottom is the variable with which we are taking the derivative with respect to. So this could be whatever variable you have in your equation. Just make sure that you understand that if you have a function that changes with multiple variables, let's say f was a function of position and time, this is going to be a little bit different. So we're going to start simple. If you have gone to a place in calculus, or if you're curious about how this works, please let me know and I can make a video on that as well. But that right now is beyond the scope of this video. So when you combine these two, that's what you get. And you can keep doing this. So you could do d dx of d squared dx squared of f of x. And then you get d cubed f of x over, what you think? Yeah, dx cubed. So you could do that for an infinite number of times. You could have d infinity of f of x, oh my gosh, times d, or divided by dx to the infinity. A lot of functions will go to 0 by this point, but a few special functions, like for example, if you were to do this on the function f of x equals e to the x, this would just be e to the x. What? Yes, it's pretty wild, right? Math is super cool. Okay, but what does all this mean? You're like, oh, okay, I see all these symbols and all this shenanigans. What does this actually mean? So when we are taking the second derivative, it means we are asking, how is the first derivative changing? Okay, so that the actual meaning of that will depend on what our function is. So if we are looking at position over time, just like we did in the first derivative calculus video, in that first one we had a straight line. I'm going to say this is position, which is a function of t. And in this case, our position was we can represent our position at any given time with the straight line formula where we have m times t. And we found that this was changing, our position was changing at a rate of the slope. So the physicist in me really likes to do this generally without numbers. If you prefer numbers, go back to the first video. So basically what this says is that our velocity is constant, meaning our position is changing at a constant velocity. If we were to take the second derivative, we would just get 0. And so that means that we're looking at, like, remember what I said, the average velocity. If this was actually our velocity, it would mean that our velocity was constant, and therefore at any given point we are not accelerating or decelerating. The real world is a little more complicated than that. And as most of you know, you can't really drive a car without, like pushing the gas pedal to accelerate or pushing the brakes to decelerate. I have some friends that have a hard time maintaining this, and I'm like, it's okay, you don't only have to accelerate or decelerate. You can cruise too. Okay, anyway, so let's look at something that is a little different. It will give us some information about the acceleration. So acceleration is how the velocity is changing over time. So we'll use a bit different example. So let's say that in this second trip to my friend's house, the traffic was really bad when I first started, but then I was able to clear out of the traffic and I went pew and got to my friend's house way quicker. I'm going to keep this general again. So let's say that the function of this, the function of my position over time is at squared. And since I'm starting at the origin, 0, 0, there's no other term there. And so now we can ask, okay, well, how is our position changing over time? To do that, we take a first derivative. And I realized I was doing the prime notation, my bad. Well, actually, I'll keep using that for now. So what we would do, I'll write it out though. Again, we do d dt of our function p of t. I guess I don't need that one. And then we get the 2 comes down to a t. And so if this is the graph of our position, we can draw the graph of our velocity and ask, how is the velocity changing? So this is time. This is going to be the first derivative of our position. And so in this case, we end up with a straight line. Boop. A straight line with the equation y equals 2at. Okay, and so now we say, okay, well, this is kind of interesting because our velocity, I should say, this is our velocity. Whoops. Boop. Our velocity is a function of time. So that's a little counterintuitive because it means that our velocity is changing. So not only is our position changing over time, which you could probably guess just by looking at this, but our velocity is changing over time. Well, how much is our velocity changing over time? And how is it changing? That is where a second derivative comes into play. So to find out how the velocity is changing over time, we just take a derivative of the velocity. And so the good news is that the derivative rules are always the same. So no matter what function you have, when you take d dt of v of t, all of those rules are still the same. So this actually equals d squared of, of p of t, because vt is dp of t dt. So there's a few different ways to write this. I like this because it helps me acknowledge that I am trying to find the change in velocity rather than the second change of position, which can be a little confusing. But if it helps you to remember that we're taking the derivative of a derivative, that's cool. use whatever notation is most comfortable and familiar to you. So to do this, we apply the same power rule. So this is just going to equal t to the 1. 1 comes down, you just get 2a, and then t to the 0, which goes to 1. So our acceleration over time is 2 times a. And that's a little confusing, but I'll differentiate by saying a of t is acceleration. Okay, and so now we can ask, what does that look like? So again, t is on the horizontal axis, and we have p double prime of t, which is just going to be a straight line. Because in this case, our acceleration, a of t, equals 2a. So this could be, I don't know, g or something like that. The acceleration due to gravity on Earth, which is constant. So in this case, there are a few things that we can say about how the velocity is changing. First of all, the velocity is changing at a constant rate, which means, in other words, our acceleration is constant. The other thing that we can say is that our velocity is increasing, so we are speeding up. I had my foot on that gas pedal and not on the brake. If, on the other hand, my picture looked like this, ooh, I'm gonna get another color. I always forget I have extra colors. Okay, so if instead my position looked like this, then I would have a line that looks like this, and my acceleration would be down here. And so by looking at either one of these, we'll call this v2 of t or a2 of t, hopefully y'all can see that. So in this case, if I saw either one of these graphs, I could say, oh, okay, our acceleration is constant, but it's negative, which means that our velocity is decreasing, aka I had my foot on the pedal that whole time. So then you'd be like, well, how did you start moving? That's a different question. But yeah, so if you saw a negative acceleration, you could say, okay, we are decelerating. That's it. Pretty cool, right? So again, the general way to look at a second derivative is just, it is the way, it is how much the first derivative is changing. Likewise, a third derivative is how much the second derivative is changing, or how much the acceleration is changing. Once you get to higher and higher order derivatives, it can be hard to keep track of what is actually happening, but it helps to just remember that a derivative is asking how a particular function is changing. And then you say, okay, well, changing with respect to what? It depends. That's what this variable tells us. So in this case, we're asking how is position changing with respect to time, but we could theoretically also ask how is position changing with position. Might not make as much sense or give us any really useful information, but we can ask that if we want to. So the key thing here is to keep track of what your question is and where you're at in that answering process. Okay, so I'm gonna leave it there for now, but please let me know if you have any questions about second order derivatives or higher order derivatives. In all honesty, you just repeat this process for however many number of derivatives you have to take. And again, this is a full derivative, but there's only one variable, which means it's a lot easier to deal with. If you would like me to talk more about derivatives, that's cool too. But I also have gotten a request for talking about Fourier transforms, which are super cool. So unless I hear from other folks in the meantime, I will plan on doing that. All right, so thanks very much for watching, and we'll see you next time. Bye!